Welcome back to AI.Code.Cast, where we, love to dive deep into these coding challenges that we all face today. We're going to tackle one that's a classic. It might seem simple at first, but it really gets you thinking, gets those problem-solving gears turning. It's called the move zeros problem.
Yeah, it's a really good one. It makes you think about efficiency and how we use memory when we're manipulating arrays, right?
So imagine you have an array. It's full of numbers. Some of those numbers are zeros, some aren't.
Mm.
Our goal, what we got to do is move all the zeros to the end of the array.
Mm.
But there's a couple of rules, right? We can't just randomly move them around. First rule is we can't change the order of the other numbers, the non-zero numbers.
Hmm.
And second, we have to do it in place,
Yeah,
meaning we can't create a new array. We've
right.
got to work with the one we've got.
Right, that in-place requirement. It adds a nice layer of complexity because you have to get clever about how you're shuffling those elements around. And it's something that um, comes up in real-world scenarios a lot where memory might be limited. So,
Right, yeah, I can see that. Okay,
yeah.
so if I was approaching this for the first time, my first thought, just off the top of my head, might be to just create a new array. Copy all the non-zero numbers over,
Yeah.
and then just fill the rest of that new array with zeros. Seems pretty straightforward, but I'm guessing there's a reason we're not going to do that.
Yeah, you're spot on. That's what we call a brute force approach. It works, but it's not the most efficient way.
Yeah.
The problem with creating a new array is it uses up extra memory, especially if you have a really large array. And we want to be mindful of those memory constraints, and doing things in place helps us conserve that memory, right?
Makes sense. So if we're not making a new array, how do we even begin to move these zeros around without disrupting the order of the other numbers?
Well, let's think about what we can actually do, what we're allowed to do. We can only modify the existing array, and we got to keep the non-zero numbers in order. So what if we had some way to swap elements within the array? To achieve our goal,
Swapping elements. I like it. Is that where this idea of pointers comes in? I heard pointers can be pretty handy for manipulating arrays.
you're on the right track. Pointers are really useful for keeping track of positions within our array and guiding our swapping actions.
Okay, this sounds interesting. But how would we actually use pointers to solve this problem? What would they be pointing to, and how would that help us move those zeros all the way to the end?
Well, imagine we have two pointers. We'll call them left and right. They both start at the beginning of the array, ready to rearrange those elements.
Okay, a pointer dance, I like it. Tell me more about this choreography. What are these pointers actually doing?
So picture this. Our right pointer. It's like a scout. It moves through the array inspecting each element, and its job is to find those non-zero numbers. Meanwhile, our left pointer. It acts as a builder, making sure all the non-zero numbers the right pointer finds are placed nicely and sequentially at the front of the array.
Okay, so if the right pointer comes across as zero, it just keeps going, right?
Yeah.
It only cares about the non-zero numbers.
Exactly. The right pointer's only looking for non-zero elements. But here's the cool part. When the right pointer does find a non-zero number, it signals the left pointer, like saying, hey, I found one, let's swap it with whatever you're currently pointing at.
So they swap positions,
Yeah.
and the non-zero number moves closer to the front of the array. What happens next? Do they both move forward?
Exactly. After the swap, both the left and the right pointer move forward one step and are ready to keep going through the array. And remember how we want to keep those non-zero numbers in their original order? This swapping action helps us do that while simultaneously moving the zeros towards the back.
This is starting to make sense. So the left pointer is like a gatekeeper, making sure all the non-zero numbers get through to the front of the array, while the right pointer scouts ahead for more. But I'm still a little fuzzy on how this actually gets the zeros all the way to the end. Do we have to move them there specifically?
That's a great question, and that's the cool thing about this approach. We don't explicitly move the zeros. As the left and right pointers do their thing, the zeros are naturally pushed towards the end of the array. It's kind of like if you imagine a crowd shifting to make space for someone trying to get through. The zeros are kind of being crowded out as the non-zero numbers move to the front.
Okay, I think I'm starting to see how this works. The two-pointer approach, it's pretty neat. It's simple, seems efficient too. We're only making swaps when we need to. It's not like we're creating a whole new copy of the array or anything. But how do we know when we're done? When do the pointers stop their dance?
Good point. The pointers know they're done when the right pointer reaches the end of the array. It's like, at that point, the scout has seen the whole thing and made sure all the non-zero numbers have been moved to the front.
And since the zeros kind of get pushed to the back along the way, we don't have to worry about putting them there ourselves.
Right. The zeros will have filled in the rest of the array.
That's really cool. I'm really starting to see how powerful this technique is, but
Yeah.
you mentioned earlier that there are other ways to solve this problem. Is there another approach we could talk about? Maybe one that gives us a different way of thinking about it?
Absolutely. There's always more than one way to solve a coding problem, and looking at different approaches can help us learn more.
So what's another way we could move these zeros to the end?
Well, there's something called the single pass counting method,
Yeah,
and it's all about trying to touch each element as few times as possible.
single pass.
Yeah.
That sounds cool. If we can do it all in one go, how would that work?
Okay, so imagine we have our array, but this time we only have one pointer. We'll call it last non-zero found it. It starts at the beginning, just like our left pointer before.
Okay, so last non-zero found it. It's like our bookmark.
Right.
It marks the spot where the next non-zero number should go.
Exactly. It's reserving a space for the next non-zero number we find. And then, here's the neat part. We go through the array just once, looking at each element one by one.
All right, I'm with you so far. What happens when we see a non-zero number during this pass?
That's where last non-zero found it is important. When we find a non-zero number, we put it right into the spot last non-zero found is pointing to.
Oh, okay. So we're not swapping this time. We're putting the non-zero numbers right where they need to be.
Exactly. No more swapping. It's all about being efficient. And here's another interesting thing. If we come across a zero, we just ignore it and keep going.
Wait, we just ignore them. So they basically get left behind as we fill in the array with non-zero numbers.
Yep. But the important thing is, as we place the non-zero numbers, we also move our last non-zero found a pointer forward, so it's always pointing to the next open spot.
This is making sense. So by the time we've gone through the whole array, all the non-zero numbers are at the front in the original order, and last non-zero found at is pointing to the spot right after them.
Exactly. And now, we need to take care of those zeros. We go through the rest of the array, starting from last non-zero found at, and just fill it all in with zeros.
Like a cleanup crew, making sure all the zeros are at the end.
Exactly. So it's a two-step process. Place the non-zero numbers, then fill in the rest with zeros. And we've done it all in one pass through the array.
This single pass counting method is pretty impressive. It seems very efficient. We're only writing to the array when we absolutely have to. But how does it compare to the two-pointer method in terms of how efficient they are? Are they about the same, or are there situations where one is better?
That's a great question. And the answer is, it depends. Both approaches have their pluses and minuses.
So what are some things we should think about when deciding between the two-pointer swap and this single pass counting?
One thing is, how are the zeros spread out in our array? If there are only a few zeros here and there, the two-pointer swap might be a bit faster, because it doesn't need that second pass to fill in the zeros at the end.
That makes sense. But if we have a ton of zeros, especially if they're all bunched together, the single pass method might be better, because we're only doing something when we find a non-zero number.
Right. The single pass method is great when we can do as little writing as possible.
So it's a trade-off. The single pass method has that second pass, and the two-pointer method might do some unnecessary swaps.
Exactly. And this is why it's important to understand our data and what we're trying to do. There's rarely a perfect solution in programming.
This has been really interesting. It's kind of cool how a problem that seems so simple can lead to all these discussions about algorithms and efficiency. We talked about brute force, the two-pointer swap, and the single pass counting. But I remember you mentioned another approach, something about an optimized swapping technique. I'd love to hear more about that.
Yeah, you're right. There's one more optimization we can do. It's like a refined version of the two-pointer swap to make it even more efficient.
Okay, I'm all about optimizing. What's the secret to this refined swapping?
So let's think back to how the original two-pointer swap worked. We had left and right. And when right found a non-zero number, we swapped it with whatever was at left. But what if left was already pointing to a zero?
Yeah. That does seem a bit redundant. Swapping a zero with another zero doesn't do anything. Just moving zeros around for no reason.
Exactly. Those extra swaps might not be a big deal when we're talking about big O complexity, but they can actually slow things down, especially with really big arrays.
So this optimized swapping tries to get rid of those extra swaps.
Exactly. It's about being smart and only swapping when it helps move non-zero numbers forward.
Interesting. How do we do this selective swapping? Do we change how the pointers work?
The main idea is the same. We still have left and right is still looking for non-zero numbers. But now, before we do a swap, we check something. We ask, is left currently pointing to a zero?
So we're being more careful about when we swap. If left is already on a zero, we just skip the swap. because we want those zeros at the end anyway.
Right. And instead of swapping, we just copy the non-zero value from right directly to where left is pointing, and then both pointers move forward.
I see. We're basically ignoring the zeros on the left
Yeah.
and only swapping when it actually moves a non-zero number closer to the front.
Exactly. This can really speed things up,
Yeah.
especially when there are lots of zeros together.
This has been an awesome deep dive. We started with a simple problem and ended up talking about all sorts of solutions, each one with its own little quirks. It's amazing how much there is to think about, even with simple coding challenges.
Yeah, it really shows how cool computer science is. There's always room to be creative and make things better.
Well, that's all the time we have for today's episode of AI.Code.Cast. We covered a lot of ground with the move zeros problem, from brute force to two-pointer techniques, single-pass algorithms, and even optimized swapping. We learned that the best solution depends on the situation. To our listeners out there, we encourage you to try these different approaches. Play around with different arrays, see how they work. And remember, the process of solving the problem is just as important as the solution itself. Keep coding, and we'll see you next time.